So today is our last lecture on Wednesday, and there's no more labs. So you are done with the lab. So the only basically remaining thing in the course is this lecture today and your test 4 on Wednesday. So and the test 4 on Wednesday is in your scheduled class time. Because on Wednesday we are following the Monday schedule, what that means is that this section B, your test is at 4 p.m., the same time as this lecture. So that you want to have on Wednesday. You have to go to your own section, do the test that is posted for section B at 4 p.m. on Wednesday, because you're going to be actually graded by the test cases and everything from section B. So if you go to do a test of a wrong section, all the test cases are going to fail. So you have to go to do exam that is meant for your section exam, test 4. Okay, by the way, about the grades for test 3, there are still a small number of students that don't have their grade. Hopefully you will all have your grade by the end of today. I asked TAs to make sure that by the end of today, everything is graded. So hopefully today, those last few students without the grade, those few students without the grade will have their grade by the end of the day. One last thing that I would like to point out, and then I think it's important for all of you, in fact, all of you who will be taking the next course in the next semester. So ITI 1121, majority of you, in fact, all of you who are in computer science or in software engineering, you will be taking this course. As you know, this course is in Java. And importantly, it's not like you're going to repeat this Python course, but everything in Java. You just continue with the material. So in some ways, it's almost expected that you can just jump into test transition, which is actually not such a big expectation, in the sense that it's the problem-solving skill that you are learning in this first course, in the ITI 1120. And you continue ITI 1121. Having said that, it's still, there is something to learn. You need to learn the syntax. It's quite different, Java syntax, from and limitations that it has and rigor it has. It's much bigger than in Python. So for all of you who haven't programmed in Java before, and in fact, even for those who did, I suggest 2 things. One, if you haven't programmed in Java before, you should read a textbook. Make sure that you're ready for ITI 1121, because as I said, they basically just continue. And one way to do it, there are 2 things for that I recommend. So basically you have about 3 weeks, probably more, before the end of the next semester. And I'm assuming that your other courses, there's really nothing to prepare. So you can have lots of rest, but take a couple of hours a day to put yourself in a great position for the next course. And to do that, first of all, a couple of years ago, I recorded 2 lectures about transition from Python to Java. So you can think of it as a gentle introduction to Java for those who know Python. It focuses on differences but it starts even from how do you write your first Java code, how do you compile it, how do you run it, then to all the way to differences and how do you do loops and everything, comparing to Python. So first of all, you will have these 2 lectures that you can, that I strongly recommend that you view, because it's not like, it's comparing it to Python, so it should be easier for you to relate. And then, of course, to find a textbook, I can recommend some and do extra reading. That's one. And then for everybody, you should redo assignment 4 in Java. In fact, for years now, that's the assignment that I share with the professors in ITI 1121. And most of the years they gave that as your first assignment. So not only what you're going to achieve during the break is that you're going to put yourself in a position to succeed in the next course by learning Java, and also you will have done lots of work that allows you to do assignment number one quickly. So if you do these things, you're going to be in great position to do great in the course. So these are my recommendations. I will post all of this on Brightspace, first of all, as an announcement, including the links to my 2 Python to Java transition lectures, and again, repeating which assignment you should redo in Java. It's assignment number 4. Okay, so that is all that I have for administrative things. What we're going to do today is we're going to finally do sorting, in particular, efficient sorting algorithms. That, all right, so first thing I'm going to explain how to do merge sort. So hopefully merge sort is one of the efficient sorting algorithm. In fact, it's not possible to be more efficient than other than up to a constant. But in terms of asymptotic big O analysis, this is the optimal sorting algorithm. You can algorithms that are faster asymptotically than merge sort do not exist. We can prove that. So I'm going to first explain that algorithm, and we are going to implement it. I waited for recursion because recursive implementation is way simpler than iterative implementation. In fact, I will share with you iterative implementation on Brightspace, just to see that it's really a non-trivial thing to do, to make sure that it's both correct and that we have the running time that we want. In recursion, this is much simpler to implement, and you will see it actually. The recursive part is basically a 4-line program. But first, let's understand what this merge sort, how it works. Hopefully, all of you, if not all, the majority of you watched the lecture that was about sorting that I posed as an extra material, not extra, it was mandatory material, but it wasn't a live lecture. It was about 30-minute lecture on sorting. In that lecture, I explained selection sorts. These type of algorithms like selection sort are typically, if you ask somebody, how would you sort? I give you a bunch of cards in a line and they have numbers, how would you sort them? So these type of procedures is something that students and people in general come up with. And something like a merge sort, it's not so easy to come up with. It's very unlikely that you just come up with a merge sort. In fact, that I haven't seen yet, that somebody just straight out, unless they knew it, come up with this algorithm. Okay, but if you remember something like a merge sort, something like selection sort, the way it works is that, okay, you find a minimum, you go through the list, you find a minimum, you know that the minimum should be in the first position, so you swap the minimum and whatever was in the first position. So you have like 2, 7, 3, 5. And then now that you have, now we know now that the first element is where it should be, and we repeat the procedure in the remainder of the list. Again, in the now remainder of the list, excluding the first element, you look for the minimum. It should be at the beginning of the remainder of the list. If it's not, you swap it. So these two would be swapped, and we end up with a list 2, 3, 7, 5. And now the second element is again correct. And then you repeat the procedure with the remainder of the list. You find the minimum, put it where it should be at the beginning of that sublist, and so on. Okay, so that is a selection sort that you have seen in the lecture. You have seen another sort, I think, in the labs. Okay, and selection sort, sort does roughly n-squared operations. Okay, so let's see what merge sort does. All right, so let's, oh, so let's look at it as an example. Something like that. Let me make sure that I have, what example did I have in my notes? Oh, wrong side. 7352. 7352. Okay. So let me use the same example. All right. So we want to sort seven numbers. When we're talking about sorting in Python, we are typically assuming that we are sorting a list. Okay. So we have a list, in this case, of 4 numbers. So the first step of a merge sort algorithm is to convert this list of 4 elements into 4 lists of 1 element. Okay, so what we do, we have a list containing 7. So for each element, you're going to create a list containing just that element. Okay, so that's the first step, and let me call that round 1. So in round 1, we take each element of the big list, list L that we want to sort, and from each one of them, we create a list with a single element. Okay, so that's what we have. So basically, this is the start. This is where we start our algorithm. Okay, and we're going to repeat, in each round, we're going to do something. Something that we're going to maintain in each round is that we're going to have a bunch of lists, but each has to be sorted. So in each round, the lists that we have are sorted. So let's make sure that this is true in round 1. Well, our lists have only 1 element, so they're trivially sorted, right? Each list that has only 1 element is sorted. Okay, so in round 1, the lists are sorted, and we are maintaining what is called invariant. We're maintaining that. And in each round, the lists we have are sorted. Okay. So now we have a bunch of lists, like in our example. What you do, you pair them. Okay, so we pair, let's say, these first 2 lists, and then we pair these 2 lists. Okay, once we pair the lists, we merge them such that the resulting list is sorted. So we are merging 2 sorted lists into another sorted list. So in this case, when we are merging these 2 lists, we are merging a list with element 7, 1 element, and another list with 1 element. We need to determine who is first. In this case, that's easy. We just have 2 elements. We compare them. 3 is smaller, so it goes first, and 7 goes second. We do the same for the next pair of lists. We merge them in such a way that the resulting list is sorted. So that's what we have in round 2. Okay, so in round 2, now we have 2 lists. And we keep on doing this until we end up with 1 list, right? So if in each round, each list is sorted, that means when we end up with 1 list at the end, we got our result because it is sorted list. Okay, so we repeat again. So we look at all our lists that we have in the current round. Round 2, we have only 2 lists, so we pair them. We only have 1 pair. And we merge these 2 lists. Okay, so let's now that we have a non-trivial example, previously kind of was trivial, how do we merge 2 lists? So let's look at here separately this. We have 2 lists with 2 elements. One has 3, 7, and the other one has 2, 5. All right, so let's say this is list L1, this is list L2. We want to merge them into a list containing all of those elements. Therefore, the final list L will have 4 elements, and it needs to be sorted too. So it needs to have all the elements from L1 and L2 and be sorted. Okay, so let's first figure out which element can go here. What are the only candidates that go in the first position of the merge list? Can 7 be a candidate to go into the first position?
No.
Only 2 or 3 can be an option.
Exactly. Because list L1 and L2 are sorted, that means that the only candidates to go into the first position here are the first element of list L1 and the first element of list L2. These are the only possible candidates. Because the lists are sorted, everything that comes after them is bigger, so certainly doesn't go to the first spot of the sorted list. Okay, so What do? We look at the first element of the first list, first element of the second list, compare them, and take the smaller one and put it in the first position of list L. In our case, that's 2. So in that case, that means that we are done with this element. Okay, this element gets deleted from list L2. And now we just repeat. We still have a list L1 and we have a list L2, which now starts at element 5. And we need to determine who goes here. Who are the only candidates that can go in this position?
3 or 5.
Again, exactly the same answer. The first element from L1 and the first element from list L2 are the only candidates for the next position in list L. So you compare the first two elements, the first element L1 and first element of L2. In this case, 3 is smaller, so it goes in this position. Now we erase 3 from L1. We are left with 2 lists with 1 element. The only thing left to do is to compare them. 5 is smaller, so it goes here. 7 is goes here. Okay, so that's how you merge 2 sorted lists. All right, so this is the algorithm. We are going to, this is called merge sort algorithm. All right, because you keep on merging sorted lists, merge sort. But let's see, why is this algorithm, oh, what happened here? Delete, I have to restart this. All right, very good, at least it worked. All right, so this algorithm is called merge sort. Let's see, what's the big fuss? Is this really, and why is it better than n squared? All right, so let's look at a little bit of bigger example. All right, so suppose I have a list with 16 elements. All right, so in round 1, so this is going to be, we're going to have 16 lists of 1 element. Okay, so we are looking at n is equal 16k. So I have 1, 2, 3, 4, 1, 2, 3, 4, 1, 3, 4, 1, 2, 3, 4. Okay, these are little lists. My squares are lists. Okay, so we have 16 lists of 1 element. So that is round 1. All right, so here we have round 1. This is what we have in round 1. Okay, then we said to get into the round 2, you pair. You pair 2 lists, okay, until you run out of pairs. So we did that, and merge each pair into a sorted list. So we merge here. We get each one of these lists that we are merging has 1 element, so the resulting lists have 2 elements. Okay, so we end up in round 2 with 1, 2, 3, 4, 5, 6, 7, 8 lists of 2 elements. Okay, to get to round 3, we repeat. We pair our lists. I pair this one and this one, this one and this one, this one and this one, this one and this one. I pair them and I merge the pairs. So here I'm merging 2 lists of with 2 elements. Therefore, when I merge it, I'm going to have a list with 4 elements. Same here, same here, same here. Okay, that's in round 3. Okay, we're still not done. We still have 4 lists. We need to have 1 with 16 elements. So we continue, we pair the lists. Once we have the pair, we merge them. So these 2 lists that we are pairing have 4 elements. So the resulting list has 8 elements. Same here. I'm not really counting here. That's round 4. And finally, in round, when we go from round 4 to round 1, we only have 1 pair because there are only 2 lists. Each of the lists has 8 elements. So when we merge it, we end up with a list containing 16 elements, and we are done in round 5. Sorry, round 5. Okay. Okay, so what would be a running time of algorithm that does something like this? First thing we need to figure out is to go from how much work we do to go from in each round, right? So how much did it take to create, just a moment, I think my pen is at 0%, but they advertise that it charges in 10 seconds. Okay, so this was me making fluff speech to see if it does. Okay, so what we want is to see how much work, how many operations did it take us? This thing is now not showing what I'm drawing. All right. QuickTime is being annoying. All right, let's try again. New movie recording. Oh no. Oh, very good. Okay, so how much work did we do in round 1? How much to create round 1? How much work did we do to go from round 1 to round 2? Okay, okay. So what we want, the number of operations is the total number of operations of merge-sort algorithm is the number of operations in one round, in a round, okay, times number of rounds, okay? All right, so let's figure out these two things. So we need to figure out what's the number of operations that you do in a round and what's the number of rounds. So what do we do in a round? Yes, Lilia.
The merging is n operations, and we're doing it log 2 of n times.
Okay, so that's fine. So let's explain where this comes from. All right, so let's figure this out first. So when we look at a particular round, you see that, let's say we're looking round 3, you see that the main thing that we are doing is merging 2 lists. Okay, so here I'm merging these 2 pairs of lists. So first of all, to answer this question, how many operations do you do in a round? We need to figure out how many operation is merging 2 lists, one with n1 element and one with n2 elements. So let's look at something like this. So to figure the first thing out, let's say I have a list with n1 elements. So list L1 has n1 elements. And then I have another list where number of elements in that list is n2. So this is a list L1 and its size is n1, and this is list L2 and its size is n2. So we basically already covered this, but let's briefly look at it again. So here maybe we have 7, and then and both of these lists are sorted. So we are merging sorted lists in each round. So 7, 9, 22, and here we have, I don't know, 3, and then 8, and then, I don't know, 20, all right, and so on. So what did we say we do when we are merging when we are merging 2 lists? First of all, this list has n1 elements, and this list has n2 elements. So the final list, list L, is going to have n1 plus n2 elements. Okay, and to determine what are the members of this list and in which order, we have already seen the procedure that we do. First of all, we need to figure out which element goes in the first spot. And let's see how many operations we do to determine that. To put the first element in the first, to determine what's the first element that goes into L, and to put that element in L. We have, because the lists L1 and L2 are sorted, it is enough to just look at the first element of list L1 and the first element of list L2 and compare them. That's one operation. So in this case, we are comparing 7 and we are comparing 3. 3 is smaller. And you take that smaller element and you write it in the first position of list L. Okay? Writing in a given position of the list is also one operation. And after that, we have one more thing to do, which is we are done with 3 and we delete it from the list. Deleting an element from the list is a constant, but only if you're deleting from the beginning or the end of the list. And we are lucky or not lucky, there is a reason, this is the way it is. We are deleting an element from the beginning of the list, and that's again, you can say that's one operation. So how many operations did we do to determine one element in the new list? It was one comparison, then writing the smaller element in the list, and then deleting that smaller element from its original list. So this is, let's say, 3 operations, okay? And then we repeat. To determine which element to put in the second position of the list, we do exactly the same thing. We take now the first element of list L1, first element of list L2, which is now 8. We compare them. That's one operation. 7 is smaller. Therefore, we put 7 in the next position. That's a second operation. And we erase 7 from list L1. That's a third operation. So to fill each of these positions, we do, let's say, 3 operations. So the total number of operations is 3 times the size of the new list, which is N1 plus N2. So 3 times N1 plus N2. Remember, we really don't care about the constants. I'm talking about big O notation here. So it's N1, big O of N1 plus N2, where N1 is the size of the first sorted list and N2 is the size of the second sorted list. So we know, what did we learn here, is that merging two sorted lists of size N1, N2, this is size of L1, this is size of L2, can be done in O of N1 plus N2 operations. Okay, so let's go back and use that to determine this. What is the number of operations we're doing around? Okay, let's go back to our example and try to figure that out. Okay, let's figure out how much it costs us. First of all, how much did it cost us to create round 1? We have a list with 16 elements. We can just go through that list and create one list with one element. Okay, so creating a little list with one element, that's just one operation. Okay, so round 1 costs us n. If the list has, creating lists with one element can be done with n operations if the list has size n. In our case, it's 16, right? So round 1, we can obtain round 1 with 16 operations. Okay, so how much does it cost us to create round 2? So what is the thing that we are doing? We have here a list of size 1, list of size 2, both sorted. We merge them. Was the number of operations? It's N1 plus N2. Let's forget O and 3. Let's just stick to it just for simplicity. To merge these two lists of size 1, we do 2 operations. Okay, to merge these two lists of size 1, we do 2 operations. So each one, we were creating each one of these lists here of size 2 took us 2 operations. How many of these little lists we have is 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2. To get into round 2, we did 16 operations, which is n. N is our 16. Okay. How much did round 3 cost us? What do we do in round 3? We take 2 lists of size 2. So N1 is 2, N2 is 2. These are 2 sorted lists. We merge them. How many operations do we do? Well, n1 plus n2. So creating this list costs us 4. The same for creating this list. It's cost us 4 operations, 4 operations, 4 operations. So round 4 cost us 4 times 4 operations. So here we created 4 lists. Each cost us 4 operations. So round 4 cost us 16. So that is n. In our case, in our example, n is 16. Okay, round 4. To get to round 4, how many operations did we do? We merge this list and this list. They have size n1 is 4, n2 is 4. So the number of operations is n1 plus n2 to merge them. So here's 8 operations to get this list, 8 operations to get this list. So this is, this round, 16 is 8 plus 8. Round 4 cost us 16 operations, 8 plus 8.
You pause the recording again.
Yeah, okay, thank you. I don't know why it does that, but yeah, delete. All right. And finally, round 5, what we're doing, we are merging 2 lists of size 8. So n1 is 8, n2 is 8. So that's 8 plus I'm back here, 8 plus 8 here. And that's 16. So creating this final list, that's also 16 operations. Okay. So 16 was just our example. So it's roughly n. In our case, n was 16. So in each round, in fact, we do each round, we do of n operations. Okay, a round costs us of n. Okay, so let's go back here. Now we can for a moment forget that. Let's go back here. What did we learn? So this was times. This is O of n. So each round costs us O of n. So the number of operations, so merge sort. Okay, we learned that's O of n because that's what the number of operations is in one round times the number of rounds. Okay, but the number of rounds, how many rounds do we have? So the number of rounds I hope is familiar to you. So let's figure out how many rounds we have. All right, so round 1, we have n lists of size 1, but that doesn't matter. Let's try to figure out how many rounds. In round 1, we had n lists. Because we paired them and merged them, in round 2, we have n over 2 lists at most. Okay. Round 3, we paired and merged them again, we had n over 4 lists. Round 4, we have n over 8 lists. Round 5, we have n over 16 lists. Well, in our case, n was 16, so we are down to 1. So in each round, we are dividing the number of lists we have by 2. So we start with n, divide by 2, divide by 2, divide by 2, until we get something that is less than equal to 1, until we get to 1 list. So hopefully by now, this is really settled in your head, that if I'm asking you how many times can you divide n by 2 before you get something less than equal to 1, that's a definition of log base 2 of n. So the number of rounds is at most log base 2 of n. Okay, so we can replace this by log base 2 of n. And in other words, this is O of n times log n, because we have an n here and we have a log n here. Okay, so remember that comparing to selection sort, in selection sort, you had here, let's use a different color, you had n squared, which is n times n. So you're comparing this log n and this. This is exponentially smaller than. Log n is exponentially smaller than n. So merge sort algorithm does n times log n operations. We're going to run some experiments, and as we did in past, and you will see in practice how much faster it is. But basically, not only that it's faster, but this is the best possible algorithm. You will learn how to prove these so-called lower bound techniques. How do you prove that algorithm that runs in better than of n times log n does not exist? So this is the best possible algorithm. You can work on the constants, right? What do I mean by that? Remember what big O notation means. You can work on it. Oh, maybe, you know, somebody gets an algorithm and here it's like that does exactly 3 times log n, and somebody else maybe worked on it and improves it and has 2 in front of n log n. But in terms of asymptotically, there is no better than n times log n algorithm. Okay, so now that we hopefully understand how the algorithm works, let's implement it. Yes, Jason.
I just have a quick question. So I get why merge sort is O(n), but when it comes to log base 2 of n, if n is 16, then shouldn't that mean like it shouldn't run 4 times instead of 5?
Yes,
Because there's 5 rounds.
Yeah, there's always +1. There's all in this log base, because there is +1, but we are ignoring the constants. It's log base 2 of n +1. But because we're ignoring, yes, you're right. It's log base 2 of n +1.
Okay.
Okay, thank you. All right, so let's implement this, and you will see actually how easy is this to implement in Python. Sorry, not in Python, using recursion. Well, in Python too. When we were doing this course in Java, I wasn't implementing merge sort, and the next thing that we're going to do, which is quick sort. Okay, so given that I already coded merging of the two lists, because this merging of the two lists, I'm not going to do recursively. This is just a procedure that I need. I need a little sub-problem. In other words, I need a function that given two lists, sorted lists, and L1 and L2 returns a new list, which is a merged L1 and L2, right? So there's no reason to use recursion for that. There is nothing new for you in terms of implementation of that. So I already pre-coded it. I can show you the code. So here we have a function that given a sorted list L1, let me put this down. All right, so given a sorted list, L1 and sorted list L2 returns a new list, which is a sorted, which is a merged L1 and L2 sorted. So here, instead of deleting actually the first element of the list, of each list, L1, when we find an element, the smallest of the two front elements, instead of deleting the smallest one, I just keep indication of where is the beginning of the new list, rather than doing deleting, which is really unnecessary. You can just keep a variable saying beginning of my list is in position 3 of the list now. Okay, so it's these two variables that do that. So I1 keeps track of where is the beginning of the list in L1. I2 keeps track of where is the beginning of the list in L2. This is a new list that we are trying to create. And you repeat this as long as I1 and I2 are not the last element in some list. So if you come to the end of one of the lists, then there's nothing to loop. There's nothing to do anymore, basically. So that's what you're going to be repeating. So what you do is just compare first two elements in the list. So I1 is telling you take the first element of list L1. I2 is keeping track of where is the first element of L2. You compare them. If L1 is the element of L1 is smaller, you add it to the new list and you advance the beginning of the list to the next one. Otherwise, you add the first element of L2 to the list and you advance the beginning of the second list to the next element. So that's basically it. There's nothing to this part here. Just if one of the list is finished, you just add everything from the remaining list to the end. Okay, so there's really nothing new here. This is just implementation in iterative way of what we discussed, how you implement merging of the two sorted lists. So that is that linear or NON. So this is that O of N1 plus N2 solution, where N1 is number of elements in L1 and N2 is number of elements in L2. Okay, let's now implement an actual merge sort algorithm, given that we have this helper function to help us merge two lists. Okay, so we want merge sort. All right, so we have a list L. By the way, one of the things that you have to decide, or whoever's asking you to do this decides, is do you want to sort the original list or you want to sort a copy of the given list? So I opt for sorting a copy of the list. Therefore, I'm going to return a sorted copy. If you were returning the original list, if you were sorting the original list, there is no reason to return anything. So you just put none. The original list will be sorted. In our case, we are returning a copy of the sorted list. Okay, so let's put our recursive hat on and do those two steps that I was explaining in last two lecture. Remember, the first thing to do is, when is there nothing to do? When is the list already sorted? Anyone?
When there's
when it's
one
empty.
list.
Yeah, so when the length of the list is at most 1, there's nothing to do, just return a copy of that list. Okay, remember that this type of slicing creates a copy of the list. If I put return L, I would actually be returning the original list, but that's technicality now that I don't want to go into. So that is the part. We are done with that part. If the list has 0 or 1 elements, there's nothing to do. You return a copy of that list. It's already sorted. All right. So now you ask yourself the second question. How do I split the problem, or how do I express the problem to big solutions? So how do I express a problem of sorting a bigger list in terms of sorting some smaller sublists? All right. So what is the most fair division of work? Imagine somebody gives you, I'm going to take we already discussed this type of thing, and by now, hopefully you can at least just guess that you should try to split the problem, if you can, into 2 smaller problems of roughly equal size. Okay, so in this case, we have a list with an element. Well, then in that case, why don't you, if I'm giving it to students, I only have 2 students, let's say, I give half of the list to one student to sort, and in the next half of the list to the other students to sort. Except that we are not giving it to students, we ask Recursion to do the job for us. Okay, so I'm going to call merge sort on the first half of the list. In fact, I can even compute where is the middle of the list. Middle of the list is len of L into division 2. All right, and I can just then call merge sort to sort the first half of the list. So from the beginning, we use slicing to the middle. Go from the beginning to the middle and sort the first half of the list. And I'm gonna call that sorted list, I'm gonna store it in L1. Okay, I do the same with the second half of the list. I make a recursive call to sort the second half of the list. So I start in the middle and I go to the end. So slicing, I start in the middle and I go to the end. And the sorted version of L2 of the second half of the list gets stored or referenced by variable L2. So now, once we end up here in this position, L1, the first half of the list is sorted and stored in L1. The second half of the list L is sorted and in list L2. Now we just call our procedure that we have, our helper function, to merge those two sorted lists. So we do return, I call merge. So I call this procedure here to merge my L1 and L2. Okay, so let's see if that's it. Other than these trivialities like computing the middle and returning the list in case of the list has 0, 1 element, this is 3 lines. Okay, all right, so let's see if it's working. Hopefully I didn't make mistakes. All right, so I stop this just to run this on a smaller example. All right, so 7, 5, 2, 3. I send that list to merge sort. 2, 3. All right, and you see that it's working, that it is sorting the list. When you look at this code, you may say, wait a minute, when you were explaining, and let's go back to the drawings if I still have them. When you were explaining quick sort, sorry, not the quick sort, it's going to be next, the merge sort, you told us that the first thing you do, you are creating this list of size 1, and where is that here? Recursion does it for you. It's just hidden in the way this is written. But let's look at just one example where a list of size 1 is created. So what was the example here? Let's look at this one, 7523. So imagine your list L is first time you call quicksort, L is 7532. So you come here, it doesn't have size 1, middle is computed, but then here you're calling merge sort on the first half of that list. So the list here that you are sending to the next merge sort function running is a list with 7 and 5. So merge sort starts running where this list L has 7 and 5, 2 elements. So it's not 1, so it skips this. And now again, we come to a call to merge sort function. The function, the list L, where we come here, L had 2 elements, 7 and 5. But this merge sort call starts a merge sort in the first half of that list. The first half of that list that has only 7 and 5, the first half has only 7, okay? So here we are calling merge sort with the list of size 1 that contains only 7. So that one starts running here. We are now in the case that list is size 1, so we return it because it's already sorted. Then the function that was waiting makes the call to this, which the function that was waiting was the one that has only 7 and 5. And now it sends the second half of that list, which is just a 5, a single element with a 5. So through the run of this recursive call, these singleton lists are created. So I hope that you should put this in Python visualizer and run it, and you'll see how these lists of size 1 actually are created through the runs of these recursive calls. Okay, so that's all I wanted to show you about merge sort. We're going to run experiments later, and we're going to see how it fares both with selection sort that we know is quadratic, but also in comparison to Python sort. But before that, we're going to implement another famous algorithm. So this is all famous algorithm. Merge sort is a famous sorting algorithm. We are going to, so then we are done with merge sorts. What we're going to do next is we are going to implement another famous algorithm called quicksort. In fact, it's so famous that it's basically implemented in every programming language, okay? And the quicksort is even way simpler than merge sort. And it's based on randomization. So it's actually the first randomized algorithm, efficient randomized algorithm that you're gonna see. And there are many of those. that the randomization is a very powerful technique that allows for some simple and efficient algorithms. So this is the first time you're going to see one. So here's how it works. It's really simple. Where's this is what I'm looking for. All right. So we're going to do it also an example. Let me pick the same example that okay, so it's this example here that I was doing in the other class. All right, so let's say that we want to, I'm going to explain the algorithm and then we're going to, it's also recursive implementation is way simpler than iterative implementation. Okay, so I'm going to explain a main step. So let's say this is a list that you want sorted. So these are the elements we have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Not that that's important. So what you do, you pick an element from this list at random. You just pick random elements. So let's say we pick poof element at random and it turns out to be 8. Okay, I pick an element from this list at random. As you know, in Python random module, there is actually a function called choice that allows you to pick element from a list at random. So we're going to use that one when we're doing implementation. Okay, so suppose a random element that we picked, that was picked from this list is 8. Because I'm going to need it, I'm going to store it in variable x. All right. So I'm going to now create 3 lists, 3 very simple lists. One is going to contain all the elements that are strictly less than x. One is going to contain all the elements that are equal to x from L. The other one is going to contain all the elements from list L that are bigger than x. Okay, so we need 3 lists. One is LT less than, all right. One is EQ for equal, and one is GT for greater than. Okay, so let's go through the list L. So let's go through the list L and determine where each element goes. All right, so let's go here. 22 is bigger than 8, so it goes to greater than. 2 is smaller than 8, so it goes to less than. 8 is equal to 8, so it goes to equal. 3 is less than 8, so it goes to less than. 1 is less than 8, it goes to less than. Minus 1 is less than 8, goes to less than. 13 is bigger than 8, goes to greater than. 8 is equal to 8, so it goes to equal list. And 7 is less than 8 and goes to less than list. So we are done. Okay, so that's the main procedure. So let's first implement this and then see, then what? There will be just one more line left of quicksort after we implement this. And this is easy to implement, I hope you see. So, but let's implement it. Okay. All right, so QuickTime, not QuickTime. I keep saying QuickTime because I'm all day struggling with this QuickTime software in Mac. Quicksort, all right, so def quicksort. Or actually QS, because in the other section I called it QS. QS for quicksort. Okay. The input to the quicksort is a list. Let me call it A, so it's not always L. Okay, A is a list. So let's say again that I want to return a sorted copy of that list. So A is a list. I want to contain a list that is copy of A, but sorted. All right, as always. All right. What's the first thing to do? You deal with the case. So actually, we shouldn't be even looking. It has nothing to do with, we're not going to be using this merge procedure. That's why I'm just removing it from the screen. All right. There you go. So this is standalone. This whole thing is going to be standalone with no helper function like that merge one. It's not a merge sort. All right. So as always, we say if length of L is less than or equal to 1, it's already sorted. There's nothing to do. So return a copy of list A. Okay. Now, let's implement that procedure that I just explained. We need to pick a random element from list A, that X that we were using. Even this algorithm is so famous that even that variable that we pick at random, that element that we pick at random, has a name. It's called pivot, right? You pick a pivot and then you split around the pivot. Everything less than the pivot, then pivot, and everything bigger than pivot. Let me not confuse you by even more terminology. Okay, so I did import random already. All right, so it's so here we pick a random element, random. It's from in random module. The function is called choice. I give it list A, and it's going to return a random element from list A. As we said, we store it in a variable X. Okay, and now we know the rest. You go through the list A. We create, first of all, those 3 lists. Typically in Python, at least, you create empty lists and then you add elements to them. So we need to create an empty less than, empty equal list, and empty greater than list. Each we initialize to an empty list. By the way, this is the first time I'm showing you that you can do this in Python. In one line, you can initialize more than one variable. Before I never wanted to show you this because I wanted to stick to the fact, to this description that whenever you see an assignment operator on the left-hand side is a variable name, right? But you can have more. So this thing here that I wrote above is identical to LT. This is just saving you, and it's specific to Python that you can do this. In other languages, you cannot do it, but just, it's a last class. I can show you this, and many of you probably already know. So this thing is the same as this. This is just a shortcut. So you create 3 lists, 3 empty lists. Okay. All right, so now we just put each element of list A in one of these 3, and we know how to do it. We go through items of a list. Okay, so we go through elements of list A one by one. For each one of these items, what did we say we do? If item we're looking at is less than X, it needs to go to less than list. So less than append item, you add item to that list. Else if item is equal to X, then it goes to equal X list. Append item to delete equal list. This is else if. Finally, if item that we're looking at, the number we're looking at, it's neither less than or equal to X, then it must be bigger than X. So therefore we add it to greater than list and item to it. Okay, we finished that part of the code, the one that we discussed. And now what? All right, so here's what you do now. Okay, so we have this element X, the one I call pivot. And we have all the elements that are less than X are in the list LT. All the elements that are bigger than X are in the list GT, greater than. Okay. What we know is that no matter how you sort, all the elements of less than will appear before X, because that's how we define less than. Less than, all of, they're not sorted. What's in less than is not sorted, but in every sorting algorithm has to put all of these elements before X. Similarly, all the elements in greater than come after X. So if somebody were to give us now sorted less than and sorted greater than, we just have to glue these 3 lists. Sorted, we can use even a plus operator. So sorted less than plus equal plus sorted greater than. All right. So what you hear here is asking if somebody was to give me sorted version of less than. Well, that somebody is a recursion. You should make call to the recursive. You should make a recursive call to sort less than. Okay, so we need to return what? Let me move this. So once we have these 3 lists, I return, I need a sorted less than. So I call quick sort on less than. Then after quick sort, after less than, come what should I put here? So I need to glue the next thing. What comes after? What should I put here?
The equal list.
Sorry?
The list EQ.
Exactly. List EQ. And we don't need to call quicksort on EQ. Remember, EQ only contains X. In our case, it was 8, 8. It could have been more 8s, but all the elements are the same in EQ. They're all equal to X, so there's nothing to sort, right? So here, we just concatenate, glued all the elements that are in EQ, and then greater than is not sorted. So EQ is sorted, so we don't call quicksort, but greater than is not sorted. So we call quicksort to sort greater than. Okay, so when this call returns, and when this call returns, what we are doing is gluing sorted version of less than to equal to sorted version of greater than, and that's exactly what we want. All right, so let me ask you this. Remember what we were saying when I'm always insist that you should express your solution, a recursive solution, in terms of a solution to a smaller problem. Why am I insisting on a smaller problem? Because you can always say sorted list L is equal to sorted list L. Okay. Why am I insisting that this problem better be smaller?
Because in a recursion, you always reduce the size of your problem, and you end up with a base case, which is in this case 1.
Yes, but the core of it is if you don't, you end up de facto with infinite list, or rather, in the way you put it, you never get to the list of size 1 and you never return. Okay, so when you're making if you started with a list A that has n elements, if you keep on calling quicksort on another list of n elements, so if you never reduce the size of the problem that you're looking at, and you only know solution in the small cases, which have a name, which is base case, you will never reach those small cases and you will never return. You're going to de facto have an infinite loop, except that with recursion in Python and other languages, you don't get an infinite loop because you're going to blow the stack and you're going to get the height of recursion error. Okay, so we need to make sure that when you're making a recursive call, that you're making it on a problem that is smaller, or on a list that is smaller than the original list. So we have 3 lists here. For which of these 3 lists we know for sure, or is there any of these lists that we know for sure that are smaller than the original list A? So if
We
list A
cannot know for sure.
Yes.
All three of them are smaller than A.
No. Let me give you an example. Imagine you have a list that just has 8, 8, 8, 8, 8, 8, 8. Then everything is in EQ. So EQ would be the same size as the original list. But luckily, we are not calling recursion on EQ. Okay, so let me repeat the question. For these 3 lists, do you know for any of them that they are for sure smaller than the original list?
The less than and the greater than?
Less than and the greater than. Why? Because we picked X from the list A, and X is not in less than, and X is not in greater than. So both lists less than and greater than are missing at least one element. They are missing at least one X. In our example that we were drawing, we were missing 2 8s. But because you pick from the original list an element, you know that that element is not in less than or greater than. So you know for both less than and greater than that they have at least one element less than the original list. So we don't have infinite loop. Okay. That brings me to another question. Why is this efficient? Let's first of all see if it's working. Did I test this one? Let me see if I tested it, if this is even working, what I wrote. All right, it seems to be working. Let's run it on an example. Let's run it on the same example. Quick sort. There you go, it seems to be working. So, can somebody tell me, so you've seen that merge sort does n times log n operations at most, right? So you guarantee that it's never gonna do less than some constant times n log n operation. What can you say about quicksort? So let's just see what happens in one run on the first call to the quicksort, because everything here needs to be executed before you even do the first recursive call. So this is easy. This is one operation. This is one operation. This is one operation. This is 3. So this is just a constant number. Let's say 10 operations. But here we have a loop that goes through all the elements of list A. So if the list A has n elements, this loop, and it does, starting list A has n elements. So when you execute this quicksort function once, you do n operations. The number of operations you do is the number of elements on the list that called it. So one call is n operations. Okay, so we analyze this cost you n operations. Then you have a recursive call, and then you have a recursive call again. So in the worst case, how many operations can quicksort end up doing?
N.
N in one function call. I'm talking in
N
total.
squared?
N squared. And here's why, N squared. When we just started, so this we analyzed, list A has n elements, and you already spent n operations here. You didn't even get to recursive calls. So we have, let's say I'm not gonna be writing big O. So let's say I'm just focusing on this loop, n operations. When we come here, now we have to do this recursive call. Let's say that when X was picked at random, let's say you were unlucky, and what was picked was a maximum of list A. If it was maximum that was picked, and let's say there was only one maximum, that means that everybody ended up in less than list. That greater than list is empty, EQ list contains only the maximum, everybody else is in less than list. So you make a call, this function starts running where the new list A has n minus 1 elements. And then this loop is gonna cost you n minus 1 at least. So next call is gonna cost you n minus 1. Okay. And let's say, so now you're running it on the list containing everything except for the max. So you start running, you come here, oops, again, it picks, by accident, it picks a max on that list from that list again. Okay, well, that means we had a list of size n minus 1. We pick a max, it goes to equal, everybody else goes to less than. So now less than has n minus 1 elements. And then this new quicksort function starts running with the list A having n minus 2 elements, because the starting one was n minus 1 minus the max n minus 2. So then this loop costs you n minus 2 operations. And we go on so on. We are always unlucky, always picking max, okay? And we only start returning when we get a list of size 1. So the number of operations done is +3 +2. This is a list of size 3. This is a list of, and only when we get to a list of size 1, it finally returns. So the number of operations in the worst case, quicksort can do. This adds up to n squared. I hope you know why. This is n squared. n plus n minus 1 plus n minus 2 plus blah, 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 that's roughly n squared. So this may sound strange. This is quadratic element. What's the big fuss? Why is this algorithm so famous? The question is, how likely is this to happen? This demonstrates the power of randomization. Basically, as n grows, the probability that this happens goes to 0. In fact, you are very likely to do a fair split of the work. When you pick an element from random, there is a very good probability that you're going to pick something from roughly middle. I don't want to define what a middle is. So then this work, if it's really from the middle, then, you know, this list less than is going to contain, let's say, half of the elements, and this list is going to contain half. It's not going to be half, but this one is going to contain a third, and this one is going to contain 2/3. That's enough to get log behavior. Okay. So you can actually formally do analysis of this, and this is one of the reasons why you should and you will take, I think it's the course is mandatory. Probability is a mandatory course for computer science students. Some of the most powerful algorithms we have and the fastest are based on randomization. So basically this algorithm, while in the worst case it runs n squared time, its expected running time is n log n times, even with a better constant in front than merge sort. I'm going to get to Kasim. So, and to know what it means, expected running time, you really need to know more about probability to do proper analysis of the running time of this algorithm. And you're going to learn that both in your math courses and in your data structure courses that you're going to have in the second semester. I will end by showing you the experiments. What I want to do is I want to compare how good are the 3 algorithms we implemented and Python sort. So we're going to compare the selection sort, the quadratic one that we coded. Well, I coded it in that video that I posted. Our merge, so our selection sort, our merge sort, our quick sort, and Python's sort. Okay, so I wrote that. This is already here. So here's what we just did. So this was selection sort that was done in that recorded lecture. This is the merge sort that we did today. It's there. This is the quick sort that we did today. And on the bottom, I have experiments where I imported time and I want to run, see how much it takes to sort. So what we're going to be sorting, I'm going to send here a list first of 100,000 elements and then 1,000,000 elements to see how fast they sort. I'll share this code. So here I create a random list with 100,000 elements, picked at random from 1,000,000 elements. And I pass that list to this function that does the experiments. So first we call merge sort. First of all, I copy that list because it needs to be unsorted for all the other call. So I call merge sort on the copy of the list. Then I call our quick sort on the copy of that list. Then I call Python sort. This is Python sort here on the copy of that list. And finally, I call selection sort on the copy of that list. Okay, so let's see how long it takes to sort a list of 100,000 elements. Okay, so merge sort is already done. Our merge sort, it took 0.7 seconds. Quick sort was better. It took about 0.4 seconds. Python sort is about 10 times better. It takes 0.04 seconds. And then we get to the selection sort, which is quadratic. And we're going to take, this would take a while. I would have to do computations, probably a couple of hours. I have to compute how long would it take. Okay, so let's do one more example. I'm going to create a list with 1,000,000 elements picked from 10 million numbers in a range from 0 to 10 million. And I'm going to send that list and run experiments on that. So let's run that. This should say 1,000,000. I didn't change the printout. So merge sort is doing something. It's taking a little bit longer to sort a list of million elements. Okay, but it's done in 8.5 seconds. Quick sort is still faster, takes about 5 seconds. Python store is still about 10 times faster. You can see even though we go from 100,000 to a million, we are still roughly 10 times. Python sort is 10 times faster. And the reason is that it's not asymptotically faster. What Python sort probably just has a better constant in front of log n log n. So let's say maybe this, our merge sort is 10 log n and n log n, and this one quick sort on in expectation is 5 times n log n, and Python sort is whatever divided by, it has a better constant, 1 times n log n. I'm just telling you the difference is in a constant in front of n log n and not in asymptotically faster, because n log n is the best you can have. So you can see here, and merge sort on a list of million elements. I don't know, what did we figure out the last time we were doing something like this? It takes like a year or something. Anyways, so that's all I wanted to show you for my last lecture. Before I take questions, let me wish you all the best of luck, first of all, on test 4, and then for your exam period in December. And then, of course, best of luck in your future, your studies, and that we actually meet each other in the next academic year in person, and we don't do this online thing anymore. So all the best of luck to everybody. So that's it for the lectures, and I will take the questions. Tassim.